Okay, for LDA and QDA, they are very similar in the sense that actually a naive Bayes, actually three of them could be derived from the same probability, that is when we consider that probability of x given y is of Gaussian distribution. But LDA, okay, we can say that all of them could be equivalent if we use f of x given y being Gaussian. But the difference is for LDA, they will assume that the covariance matrix of x given y is the same regardless of the class. So probability of x will just be probability of the covariance of x will be, okay, how should I write this? Okay, you probably can derive something like the distribution of y given xc, and that will have like a mu being like a vector here and covariance matrix being like a matrix here. For LDA, we assume that regardless of YC, you will have the same covariance matrix. But for QDA, for a different C, you have different covariance matrix. So for this one, covariance matrix will keep changing, depends on your class. But this one, covariance matrix will be the same. For all class. So that's the main difference. And because when we consider covariance being the same for all classes, then you can actually reduce this formula into some linear equation. But don't forget that, I mean, this one is like we write it in probability. If you want to derive this one, you have to take a logarithm, like compute it in the log space, then you get like a linear equation. For this one, you do the same, you take it in log space, but because you assume that covariance is different. Therefore, what you get is that you have a quadratic term that came from this covariance matrix. And therefore, you will end up with this term that's correlated to that covariance matrix that is existing. But for naive Bayes, you don't care. Like you don't care if there is assumption like that. You just take the form rigidly, like rigorously. So that is naive Bayes. So naive Bayes, on the other words, they are the most generalized version and probably the one that you don't really want to care about the computation. You want to compute it as it is. So that's why when I talk about whether or not they are parametric or non-parametric model, naive Bayes is kind of like in between, but actually they're quite rigorous. But they are not as rigorous as these two, because if you think about this one, you impose additional assumption that the covariance of each class have to be the same covariance matrix. Okay, so a little bit about the LDA. So this is the formula for LDA. Let's say that we come up with this term, right, where we want to consider probability of y equal to class C given x, and we know that the term within this term that will pretty much, let's say, being the one with high influence on what the class could be is probability of x given y. And if we replace this probability with Gaussian, which is going to be something that look like this, right? You probably end up with this exponential function. And actually, I forgot to mention that in this writing, I was actually same as probability of C equal to XC. So that is another way that I wrote this probability of Y being in class C given X. So above here is the conditional of X given Y times probability of Y being in class C. Sorry, above here I wrote it as class L, but it actually should be C. Yep. And below here is like, after you have this two, which you know that it's like probability of X given Y equal to C, but then when you multiply with this class of C, that is a joint distribution. So if you want only X, that means you have to marginalize Y out. So that being that you, okay, in the discrete case, that means that you have to sum of all that class out. So it's going to be sum of, okay, Y equal to C up until Y equal to K. Maybe if they are K class. Okay, they are C class actually. Sorry. So when you marginalize that out, that then becomes the probability of X, right? And that is this term here. So below here is simply the way that you compute probability of X. So what happened? If we compare two terms, let's say prop of Y equal to C versus prop of Y equal to L, you probably have to start to decompose what's going inside it. But we know that we don't want to consider the denominator term. So we only consider the term up here. We take the log. Okay, let me do it. Okay, we take the log. It will be 1 over 2 X minus mu C transpose sigma inverse X minus mu C, right, plus log of that pi C. Okay, what we see is that there are quadratic terms here. But the thing is, if sigma is the same for every classes, that means that X transpose, okay, I will just write what equivalent to that. So that will be 1 over 2 X transpose sigma X inverse X. So if you compare two classes that was like log of Y equal to C given X, okay, maybe, okay, I use this notation, versus log of Y equal to L given X, probably the only things that will cause difference is going to be like this term and this term, but not this one, because that will be the same for the same input. So that means that you want to consider only that, okay, and that. And also that log of probability of being that class, that is like the bias term. Therefore, once you have these, you can actually reformulate it. Like whatever that attached to X is grouped together, and whatever that's unrelated to X is going to be like a separate term. So you end up with like a linear function, which is similar to linear regression that you learned before. So that means that if you perform some kind of learning based on this function, you get beta 1 and beta 0, but beta 1 and beta 0 will be the value that correspond to this covariance matrix multiplied with the mu of being in class C, and beta 0 will be for the rest of that. But actually, it's like if you have a fixed formulation, I think mapping back from beta 1 and beta 0 back is possible, but at the same time, you may not need to do that because all you want to do is to compare whether or not you have the higher value from this term versus other classes. So you can end up just like with this. But what makes the difference is like the assumption that you make that if you are using the LDA, that means that you are using like a linear combination to classify. So therefore, your classification boundary, the boundary decision that you make will then start to look like a linear equation to separate between the two. And yes, another assumption that you make is a covariance metric that is the same for every class. Okay, yes, this is just how I start to clarify that if we have class C and class L, and if we compare probability of y equal to C versus probability of y equal to L, and if we kind of go back to that previous notation where we use the function of G, and if we put it in a logarithm, that should look like that. And if we compare that two term, right? Like if we have a negate of that first term with the second term that is like higher than 0, probably it should be identified as class C, less than class L. If it's equal to 0, that means that two classes are having the same probability. Yep. And this one, okay, I think we are going to the end of that. And this one will be what is like for training. So as I mentioned before, that if we have two classes and we start to compute the difference between the logarithm term, then actually we will end up with some linear equation, right, that we say it here. We can learn from beta 1 and beta 0. But what else can we derive from this assumption when we say that there are Gaussian distribution? Actually, from the relationship between maybe classes like this, we can actually derive for the mu for each class for your, let's say for, I think it's the mu for x given y belong to maybe each class by using sample mean. Pretty much that means that you can do some kind of average of x being x sample of class J, sorry, not sample class J, x sample, the J sample up until m divided by 1 over m, like that. So you will get that mu, but probably a little bit that is like, that has to be x of class that y equal to class K or maybe class C, I'm not sure, but it depends on how you write it, but yeah. It's being for this one. But it's like you have to know what x belong to, and then you can compute the mu for every classes. I didn't provide the derivation here, but it's kind of like this relationship of the mu is derived from the fact that if you are using Gaussian distribution, then yes, you can find a way to compute this mu by using the sample mean. Oh yes, it's, okay, I kind of recall it now. When we use Gaussian distribution for a random variable, the easiest way to compute that mean for that Gaussian random variable is to use a sample mean. And you can then also use sample variance for computing the variance for that Gaussian random variable to approximate the variance. So these will be like approximation value. For your mu and your covariance. So you can actually pre-compute all of them once you have your training samples. Alternatively, from if you were to learn it from this. But I think okay, it is like at the moment you have two ways to compute these unknown parameters. The first way is that maybe you can plug in this value based on your Gaussian assumption, where you say you could use sample mean as like an estimated value for your mu C or mu L, whatever class you have. And then you can also compute the covariance using some kind of sample variance. That's one way. But what is left over is like, what is the bias for probability of Y being in class, a certain class. So that is what is left. One way you can learn this value by using like a normal way that we've learned before, where we use a linear regression. We solve for beta 0 and beta 1 from mean square error, minimization. But also in this theory, it says that, okay, if it's Gaussian, you can also estimate these parameters as well. But I'm guessing that I'm not sure how. We will have to look at the tools that, like sklearn. What I also wonder is like, so then how did they come up with this value at the end? Like, did they compute this mu hat and sigma hat using formulation like this? And do they still need to do like a linear regression like that? That is like a question that I currently have. Not sure yet, but actually with this, everything that we've seen, actually there are two ways to compute maybe beta 1 and beta 0. So yes, we'll have to look at that. Anyway, so probably this is an example of when you apply the LDA onto, let's say, one-dimensional data set where you have only 1x, let's say. Yes, the decision boundary will be the boundary where you have maybe the separation between two classes. Let's say, okay, if I assign this as the probability of Y being in class maybe -2 and 2, and this is like probability of X given Y. Let's say if it's like that, then that means that what you have to do is that once you have some prior about prop of Y, what you might want to do is that you multiply it with the histogram of prop of X given Y. Then you're going to get something that approximating prop of Y given X. So I think that's the concept of this. And yes, if we look at the boundary decision making, I mean, after you have this LDA, you can verify what the boundary look like. I think there are tools to do that, like to check what the boundary decision look like for LDA. But yes, I will have to go back in the sklearn, but in your own time you can do it as well to check how did they compute for beta 1 and beta 0. Because all that they do is like, if you have beta 1 and beta 0, right, you can then start to decide if whether or not, like if this value that corresponds to maybe class C is higher than other class, then that's definitely class C. So it's pretty much like the linear regression that you've done before. Yeah, but I have to check how did they get this beta. For QDA, the only difference is that they start to have assumption about, they relax the assumption about this sigma. From previously, we said that if sigmas are all the same, then we get this discriminant function, that is this equation, because we will ignore that one. Because for every x, it's going to be the same. But for QDA, then it will be different. Like you have a little notation of sigma subscript c. That means that the covariance matrix will be different for each and every class of Y equal to class C. Yep. That's it for today. Next week, we will come back to this a little bit and go over QDA. And I will leave like a mock test example in the MS Team. You can have a look, but possibly it's not going to be that difficult. But you can look at the function, like the equations, or not equation, questions. Yep, it usually go back to that same questions in a way.